Hello everyone. The next chapter we are going to do is chemical kinetics. So kinetics means movement. So first of all, we'll look on the aspects of a chemical reaction which we can study. So the study of a chemical reaction uh, can be uh, done under three heads. The first is whether a reaction takes place or not. The second is to what extent that reaction can take place, and the third is at which speed that reaction will be happen. So whether a reaction will be carried or not, it depends on its free energy change, which is studied under thermodynamics. The extent of the reaction, how much of the reactants can be converted to products, that is studied under the equilibrium. And the third aspect of a reaction is speed, or the rate at which this reaction will be carried out, is studied under chemical kinetics. So it is the branch of chemistry which study the speed of reaction, factor affecting the speed or rate of the reaction, or the mechanism by which the reaction is carried out. So all these things can be studied under this chemical kinetics. So earlier in the class 11th, these two aspects have been already discussed, whether a chemical reaction takes place, what extent it will take place. Now the third is speed, and that is under this head chemical kinetics. Kinetics means movement, motion. The next is general classification of reaction on basis of speed. So on basis of speed, the reactions are of three types: very fast, very slow, and moderate. So very fast reactions are ionic reactions, which are of this 10 to the power minus 12 to 10 to the power minus 16 second time is taken by them to happen. The second are very slow, like rusting of iron. It may take from a few days to few months, up to few months also, right? So these two kind of reactions are very difficult to study. So uh, the study of the kinetics is basically for the reactions which are neither slow or very fast. Now next, variation. Why the reactions vary? Why the speed of different reactions vary from each other? The reason behind is during a chemical reactions, a bond, some bonds are breaking and some are forming. So, different bonds need different amount of energy, need different amount of energy to break, and will release different amount of energy when they are formed. Different type of bonds will release different type of energies when they are formed. So this difference in energy will result in their speed variation. Right? Now, rate of reaction. So rate of reaction is the change in concentration of either one of the reactant or any one of the product with change in time. So for any hypothetical reaction, our reactant is changing to product. So decrease in the concentration of reactant with time interval, which time is taken for a particular decrease, that ratio is equal to the rate of the chemical reaction, or increase in the concentration of product with respect to time. The concentration of reactant is going to decrease with time, and concentration of product is going to increase with time. So, for example, for this general reaction, R1 is the initial concentration and R2 is the final concentration. So obviously, the final concentration is less than the initial concentration for the reactants, because reactants are going to consume with time. So the change will result in a negative result. So change of this concentration. Change is final minus initial. So final concentration minus initial, because final is small quantity and the initial is larger. So the change is negative. And the time is final minus initial time changing. Similarly, for products, the product concentration is increasing with time. So the final concentration of product is always greater than the initial concentration, right? So this is the change in product's concentration, change in time. So the rate is equal to negative change in concentration of reactant, change in time, change in concentration of product divided by change in time. So this negative is added while writing the rate of the reaction. This negative is added because this indicates that the rate will never be negative. This change in the reactant concentration is negative because the final concentration is less. than the initial concentration. So this negative is already included in the equation in the relation, so that we can get a positive rate value in the end, because this is going to be negative. This change is going to be negative. So negative into negative, positive rate of friction. So this negative signifies that the concentration of reactant decreases with time, right? For now, example is there. Phosphorus pentachloride gives phosphorus trichloride and chlorine on heating. The rate of friction is either in the terms of decrease in the concentration of phosphorus pentachloride with time, or increase in the concentration of any one of the product. So basically, we can take the rate of friction in terms of reactant on and any of these two reactant. Now units will be concentration upon time units. So time is second and concentration is mole per liter. So it may be mole per liter per second, mole per liter per minute. And for gaseous reactions, it will be atmosphere per second or atmosphere per minute. Right. Now the average rate and interstaneous rate of reaction. So the rate of reaction does not remain constant throughout. When we we have to take rate of reaction, we will always talk about the average of that. It is similar to the driving a car from one place to another. We cannot drive the car for the whole distance at the same speed. It may be sometimes more or sometimes less. So we'll how we can calculate the speed, and we take the distance covered from position initial to final by taking the change of initial position to final position, and by noting the time of from initial position to the final. So that is average rate. And the rate at a particular instant of a time during the journey or during a reaction is known as interstaneous time, for that instant of time, for a particular instant of time. So now how we can measure it? So the interstaneous rate is measured by taking the small interval of time, that is change is approaches to zero, right? So this is how. So here is a large change for average, change in reactant concentration, change in time, or change in products concentration with time. So here we'll take small changes in terms time approaches to zero. Now measurement of rate of friction. So the measurement of rate of friction can be done by taking the concentration of one of the reactant or one of the product at different interval of time, and these values can be plotted against the corresponding lines. So here are the two graphs we get. For reactant, the concentration is going to decrease with time, and for products, the concentration is increasing with time. So this type of graph. So for taking average, we'll take two concentrations, x1 and x2. x2 is smaller than the x1 in case of reactants, and time t2 corresponding to x2 and time t1 corresponding to x1 concentration. So average rate can be taken by writing change in concentration of reactant with time, and this negative sign is for getting the rate positive. So whenever we are going to take the change of reactant concentrations, reactant molar concentrations, we put negative there in already in the equation, so that we can get rate as a positive. Now interstaneous rate for any instant during this slope will be equal to negative of dr by dt is equal to negative of slope. And similarly, in case of products, we can find the average rate by taking the two concentrations, and same as the interstaneous rate. And here is the positive slope, as it is concentration is increasing and here the concentration is decreasing. Now expressing the rate of reaction in terms of different reactant and products. Now, in terms of different reactant and terms, again, the example which is earlier mentioned, the decomposition of phosphorus pentachloride. This equation is for 1 mole of phosphorus pentachloride gives the 1 mole of phosphorus trichloride and 1 mole of chlorine. So all are 1 mole. So stoichiometric coefficient of all the reactants and products are same. So the rate of reaction can be written in terms of any of the species from the products or from the reactant side, right? But in the examples like this, where N2O5 is decomposes to NO2 and O2, here 2 moles of N2O5 is 4 moles of NO2 and 1 mole of O. So the rate of decomposition of N2O5 is minus negative, change in concentration of N2O5 with time, formation of NO2, change in concentration of NO2 with time, formation of O2, change in concentration of O2 with time. Now from here, uh, these are not equal. All these are not equal. The rate of decomposition of N2O5 is not equal to the rate of formation of NO2, and which is further not equal to the rate of formation of O2. Why? Because 2 moles of N2O5 are decomposing here to give 4 moles of NO2 and 1 mole of oxygen. Now, the rate of the rate of decomposition of N2O5 is 2 times the rate of formation of oxygen, right? And rate of formation of NO2 is 2 times the rate of decomposition of N2O5, right? So the rate of decomposition of N2O5 is twice as fast as the formation of O2, and the rate of formation of NO2 is 4 times the fast as O2. Now to get the identical value of rate of reaction in terms of any reactant or any product, so these rates of decomposition and formations can further be divided by their stoichiometric coefficient so that we can get the rate in terms per mole, right? In terms of per mole. So here the N2O5 is in the balanced chemical equation, 2 moles are there. So we'll divide by 2. And here is 4 moles are produced for NO2. 4 is there. And for oxygen, 1. So we divide by 1. So for any reaction in general, A moles of A, B moles of B, producing X moles of X, Y moles of Y. So we'll write the rate in terms of any reactant and any product by dividing the each with their stoichiometric coefficient as given in the balanced chemical equation. Right? Only then we can equate them, otherwise we cannot equate them. Next is dependence of rate on concentration of reactant. So this is the general graph for reactants, and this is for reactants, and this is for products with concentration against time. So the effect of concentration on the rate of reaction first studied in 1867 by Wage and Gulber, and they put forward the law of mass action. Now, what was that law of mass action? According to that law, the rate of the reaction is directly proportional to the product of molar concentration of all the reactants, raising each to the power as numerical coefficients in the balanced chemical equation. However, this relation, law of mass action is experimentally rejected and modified as rate law, where these coefficients, the power used here, which are the coefficients, stoichiometric coefficients of balanced chemical equation, are replaced by some experimentally obtained terms. Let it be P and Q for this reaction, and a new rate equation is formed. The rate is directly proportional to the product of molar concentration of reactant raising to power some numerical coefficients calculated experimentally. Now, they are not taken. They may be taken they may be equal to the stoichiometric coefficients of balanced chemical equation. They may not be equal to. They may be or they may not be. So these are the experimentally calculated, experimentally obtained values, right? So from here, the rate is equal to K, molar concentration of first reactant raised to power, experimentally obtained coefficient, molar concentration of second reactant raised to power, again coefficient obtained experimentally, and this equation is known as rate law. Now K is rate constant, or sometimes it is known as velocity constant also. So K is equal to rate when this whole term is equal to 1. So when the concentration terms are equal to 1, so K is equal to rate. So it is defined as the rate of reaction when the molar concentration of each reactant is taken as unit. Now, what are the features of this rate constant? Greater the value of K, faster is the reaction. Its value depends upon the temperature, and it is depending on the reacting species also. It does not depend on the concentration. It depends on the nature of the reactants, but does not depend on the concentration. It depends on the temperature. Its value directly proportional to the speed of the reaction, rate of the reaction, and its units are depending on the order. Now, what is order? Order is the sum of the parts of uh, parts of molar concentration of all the reactants as taken in rate law. So this is order. So order is the sum of the exponent parts to which the molar concentrations in the rate law equation are raised to express the observed rate of the reaction. Right. So the order is equal to, for a general reaction, any for A plus B giving products, and P and Q are the experimentally measured, experimentally obtained coefficients. So the sum of these two coefficients as given in the rate equation is equal to order. For this reaction, for this ionic reaction, the rate law equation is equal to K Br raised to power 1, Br O3 negative raised to power 1, and H ion raised to power 2. So the order is 1 plus 1 plus 2. 1 plus 1 plus 2 is equal to 4. This reaction is of 4 order. All the photochemical reactions are of first order. So the order may be 0 or any fraction. Can have any fractional value. So next, two numerical problems. So basically, you can get the question in the paper in form of definition of rate law, on order, on its values, then numerical problems also. So the kind of numerical problems you will get in the question paper are for any chemical reaction like A, 2A, 2 moles of A plus 1 mole of B gives 3 moles of C. The rate of appearance of C at time t is this mole per liter mole per second. That means rate of appearance of C is given. You have to find rate of the reaction, rate of disappearance of A. So first of all, we'll write rate, and from by taking the coefficients from the balanced chemical equation. So it is minus 1 by 2 change in concentration of A with respect to time, minus change in concentration of B with respect to time, and positive 1 by 3 from air, change in concentration of C with respect to time. Now what is given? What value is given? The given is rate of change of C with respect to time, that is 1.3 into 10 to the power 4. Here it is given. Now this is not equal to this. This is not equal to this. So now rate of the reaction will be achieved if we put this value here. This value is the value of concentration of change in concentration of C with respect to time, that is appearance of C at time t. If we put the value this 1.3 into 10 to the power minus 4 here, we'll get the rate of the reaction. Now how we can obtain the value of disappearance of A? Now we can equate this with this last. So we equate the two, and by taking this to the other side, we'll get the value of disappearance of A at time t, and which is equal to this value, 2 by 3 of this. Right? The other type of questions you can get, you can get on the order of the reaction. So order for any given rate, the order may be calculated as by taking the powers and their sum is the answer as overall order. So here again an example, order with respect to A is 3 by 2, with respect to B it is minus 1. So overall order is 1 by 2 or 0.5. So thank you for now. So